57 years ago, we went to the moon.
That's one small step for man, one giant leap for mankind.
This 21-hour and 36-minute visit to the moon changed the face of science forever, spawning 150 articles in one scientific journal alone in the 6 months after the astronauts returned to Earth.
Got it, sample.
But what appeared to many like an effortless feat was not all plain sailing. This mission nearly failed, and not just once. So, what did the Apollo 11 astronauts find on the moon, and how did they defy all the odds and make it home? I'm Alex McColgan, and you're watching Astrum Extra. Join me today as we dive back into the Apollo 11 mission for part 2 of this incredible voyage to the moon and back. In part 1, we got our astronauts safely to the lunar surface, but now it's time to get to the bottom of what they found and how they made the deadly trip home. The 20th of July, 1969. For the first time in human history, we were about to walk on another world. The astronauts had left the safety of Earth, traveled 384,400 kilometers across space, and split their spacecraft. Mike Collins was left circling the moon in the command module, whilst Neil Armstrong and Buzz Aldrin touched down on its surface in the lunar module. All that was left was to take one small step. But that meant leaving the protective walls of the lunar module and exposing themselves to a place of lethal extremes, harsh temperatures, deadly low pressures, UV radiation, and high-velocity micrometeors. To survive, Armstrong and Aldrin required more than just clothing. They essentially needed a wearable spacecraft. Enter the Apollo A7L. Its first and most critical task was preventing the pair from literally boiling to death in seconds. You see, in the near vacuum of the moon, without atmospheric pressure, water, including water in your blood, boils at body temperature. To counter this, the A7L needed to be pressurized, and this was done using 3 bits of kit. First was the pressure bladder, an airtight, rubbery layer designed to hold a pure oxygen atmosphere. Think of it as a human-shaped balloon, but a balloon under pressure expands. Too much would make any movement pretty much impossible. That's where the resistant layer came in, a high-strength nylon wrapped tightly around the bladder, reinforcing it and maintaining the suit's shape. This exoskeleton prevented the suit from bursting or ballooning, allowing the astronauts to actually bend their limbs. Pretty useful, considering they had a lot to do. Finally, there was the Portable Life Support System, or PLSS. The iconic backpack was a masterpiece of 1960s miniaturization. It was the source of the astronauts' oxygen, not only for breathing, but also for maintaining an internal pressure of roughly 3.9 psi. That's only a quarter of the pressure at sea level on Earth, but enough to keep astronauts alive. So that was the pressure dealt with. But what about the moon's vast temperature swings? As we know from last time, the moon's thermal environment is one of the most violent extremes, plummeting to minus 133 degrees Celsius in the shadows, yet soaring to 100 degrees Celsius in the sunlight. This suit needed to be ready for anything, and material scientists and seamstresses prepared for this by using layers, and a lot of them. The A7L had 21 layers in total, made from a mix of 12 different synthetic materials. Most of these were in the outermost garment called the Thermal Meteoroid Garment, or TMG. To be effective over the large heat range, inside the TMG they had to use layers of 2 different materials, aluminized kapton and mylar, both of which insulated the suit and reflected away the sun's heat. By using both, the suit benefited from mylar's superior lightweight insulating efficiency and kapton's exceptional strength and temperature resistance. Meanwhile, the outer beta cloth, a Teflon-coated glass fiber, provided a white, reflective shield against radiation and abrasive lunar dust. What I'm about to say next will sound very strange. The astronauts also needed protection from their own body heat. On the moon's surface, they were essentially working out, but there was no way to remove a layer to cool down. So, to prevent this trapped heat becoming deadly, NASA developed a liquid cooling garment worn against the skin. This network of tubing circulated cold water, wicking away heat, ensuring the astronauts didn't collapse from heat stroke. It wasn't just the heat that was a problem though, it was the invisible radiation that came with it. Without an atmosphere, the astronauts were exposed to a constant barrage of intense ultraviolet and infrared light. Protecting against this led to one of the mission's most iconic features, the gold-plated helmet visor. A 0.000000508 centimeter or 50.8 nanometer layer of real gold was applied to a polycarbonate face shield and acted as a high-tech mirror. But why gold and not silver or aluminium? Well, gold is stable, so won't oxidize or tarnish, and it's easy to work with, enabling engineers to create a thin, unbroken layer across the visor. Beyond its protective qualities, it functioned as the ultimate pair of sunglasses, dampening the blinding solar glare to allow the astronauts to actually see their surroundings. In fact, gold is so good at filtering infrared and UV light that the moon's surface would have appeared slightly more blue or green to them, not entirely grey like in the photos. All in all, the golden visored astronaut suit became one of the most iconic aspects of the Apollo mission, a visually eye-catching engineering marvel that has remained a part of the public imagination to this day. Most businesses would love to have the level of recognizability that these suits have, but if you're a business chasing the public's attention, you don't need a team of NASA engineers. You need the right website. And you can design the perfect one yourself with Odoo, the sponsor of today's video. Odoo is an all-in-one business management software with more than 45 apps that make running your business more efficient. Its website app is intuitive and simple to use. In just minutes, you can go from nothing to a fully built website of your own. You can build it easily by dragging and dropping category blocks and choosing templates that fit your needs. Then customize each section with internal content blocks. Adjust your text with different fonts and colors, and highlight key sections in just a few clicks. You can also use Odoo's AI to handle much of the heavy lifting, including writing your copy. Images and videos can be imported directly from your device, or you can explore Odoo's built-in royalty-free library. The website app fully integrates into Odoo's suite of other apps, and the best part is the first app is free for life. You even get a free domain name for 1 year, all under Odoo's one app free plan, including unlimited hosting and support. So see what Odoo can do to help your business get noticed today by scanning my QR code or following the link in the description below. Now, speaking of things that are slick and well designed, those A7L spacesuits needed to survive more than just glare from the sun or body heat. Beyond these invisible dangers lurked yet more threats, this time of a more ballistic nature: micrometeoroids. The moon is pelted by roughly 1,270 kilograms of space debris every single day, traveling at speeds of up to 20 kilometers per second. Even a speck of dust can carry the kinetic energy of a bullet, and there's no atmosphere to burn up this debris before it hits the surface, where an unlucky astronaut may be standing. To counter this, the suit's outer shell used something usually found built into spacecraft, a Whipple shield design. This is basically a series of high-tech materials arranged in specific layers to help absorb serious impact. In this case, the outer materials were Teflon-coated beta cloth and high-strength Dacron that would shatter any high-speed projectile that hit it, while the inner layers of Mylar and yet more Dacron acted as cushions, absorbing and dissipating the remaining energy. Spreading the force of the impact over a wider area ensured that the critical, pressurized inner bladder remained unpunctured, keeping the vacuum of space at bay. Safely encased within these portable sanctuaries, Neil Armstrong and Buzz Aldrin survived those first iconic steps. But the celebration was short-lived. A grueling checklist of lunar science lay ahead. and they only had 2.5 hours to complete it. It was a race against the clock. The top priority was getting a lunar sample. Within minutes of stepping off the Eagle's ladder, Armstrong collected a small amount of regolith and tucked it into a pocket on his leg. This ensured that even if an emergency forced an immediate evacuation, they would not return to Earth empty-handed. But the true scientific payload lay within the early Apollo scientific experiments package, a 48.5 kilogram suite of scientific experiments that you can see Buzz carrying here. One of the key instruments was the laser-ranging retroreflector. This simple array of quartz prisms allowed scientists on Earth to bounce laser beams off the moon's surface with incredible precision. By timing the round trip of these photons, we could measure the distance between our two worlds within a few millimeters. And measurements taken using the retroreflector throughout the 1970s helped us discover that the moon is slowly drifting away from Earth at a rate of about 3.8 centimeters per year. And incredibly, these measurements continue to this day, using that same retroreflector for gravitational wave research, most recently in 2026 by the Tianqin Laser Ranging Station in China. The other large experiment was a seismometer used to measure ground motion. This device, and the others placed after it, revealed that the moon was not a dead, solid rock. Instead, it vibrated with moonquakes. These are similar to earthquakes and are formed through 4 different methods. The deep ones, hundreds of kilometers beneath the surface, are tidal, caused by the pull of Earth's gravity tugging and stretching the moon's internal structures. The shallow ones originate just 20 to 30 kilometers down, can last up to 10 minutes, and are caused by the moon shrinking as it cools. And finally, there are 2 types that start on the surface, one caused by meteor impacts, and the other by the heating and cooling of the moon's crust as it cycles between night and day. And that one's not ideal for any future lunar base. The final scientific task that needed to be completed was collecting samples. In total, the crew collected 21.5 kilograms of lunar material, basaltic rocks, and fine dust that had remained undisturbed for billions of years. Because they had not been contaminated by life and were essentially unchanged since their formation, these specimens became our golden record of the solar system's history, containing chemical signatures of early Earth and the violent impacts that shaped our celestial neighborhood. After 2 hours, 31 minutes and 40 seconds, time was up. Aldrin and Armstrong reclimbed the ladder and the hatch of the lunar module swung shut. The astronauts had made it, pushing the limits of their life support backpacks. Despite having 4 hours worth of air, NASA slated their sortie to only be 2.5 hours long in case of other emergencies. The astronauts left behind their tools and footprints, and they carried back something far more precious, the chemical keys to our solar system's origin. Yet, the victory was only half won. Exhausted and covered in sticky, electrostatically charged moon dust, they now faced the ultimate gamble. All that was stopping them from dying a lonely death on the lunar surface was a single, untried engine. On the moon, there are no rehearsals and no hope of rescue should anything go wrong. The lunar module had 73 hours of oxygen, but that was nowhere near long enough to survive a resupply mission all the way from Earth. To get home, the Eagle had to intercept the command module, a tiny moving target racing through the blackness at over 5,000 kilometers per hour. Missing this window by even a few seconds would mean drifting into a useless orbit, or possibly worse, depending on how you see it, falling back towards the surface. In an environment with no atmosphere to provide aerodynamic lift, the crew was entirely dependent on physics. Guiding them was the LGC, the Lunar Guidance Computer. Its job was to outsmart the moon itself, calculating precise engine burns while accounting for mass cons, hidden concentrations of dense rock beneath the lunar surface, whose uneven gravity could tug the spacecraft off course. At 124 hours and 22 minutes into the mission, the countdown hit 0. The lunar module carried out a vertical rise for around 8 seconds, followed by a dramatic pitch over to nearly 50 degrees. This tilt allowed the ascent engine to push the craft downrange, gaining the horizontal velocity needed to reach orbit. Because the moon's gravity is only 1/6 that of Earth's, the ascent was feasible with a single, non-throttleable engine, but it required total precision. After the continuous burn, the Eagle achieved an initial elliptical orbit of roughly 17 by 87 kilometers, exactly as planned. The moon was behind them, but safety still lay many kilometers away. Their next task was to connect with the command module. But how do you do that when you're traveling at more than 5,000 kilometers per hour and a single degree of error could kill everyone involved? An hour after liftoff, the Eagle's thrusters fired in a sequence known as the co-elliptic sequence initiation. This circularized its path, bringing it onto a parallel track with its mothership. From here, the Eagle's hunt for the command module began. 2.5 hours later, the gap was closing. At 72 kilometers out, the Eagle performed its terminal phase initiation, a precise burn designed to help it intercept its target. Roughly 10 minutes later, through the narrow triangular windows, Neil Armstrong caught his first glimpse of the command module, Columbia. All that was left was to connect it. You might think this would be a simple task for elite test pilots, but in the vacuum of space, your eyes are your enemy. Without an atmosphere to provide haze or clouds to give a sense of scale, your depth perception vanishes. And in a realm where it is simultaneously blindingly bright and pitch black, the shadows lie to you and distances become impossible to judge. This is why, despite the combined 40 years of flying experience, the main rendezvous was assigned to a digital computer. It worked by Eagle's radar pinging out into the void and Columbia's transponder pinging back. This data fed the Eagle's primary guidance navigation and control system, nicknamed the Pings computer, allowing the machines to handle the high-speed geometry of the approach while the humans kept an eye on the instruments. Only in the final moments, once their velocities were perfectly matched, did Armstrong and Collins take control to fly towards each other by eye. But their margin for error was 0. Thankfully, at 21:35 UTC, the command module's triangular probe clicked into the lunar module's receiving conical drogue, triggering 3 capture latches. As they pumped up the cabin pressures, the 12 latches around the docking ring engaged and created an airtight, pressure-tight seal. Aldrin and Armstrong were finally safe. A few moments later, they were reunited with Michael Collins, who had been orbiting the moon alone the whole time. But there was no time for celebratory dance or high fives. Instead, they quickly began unloading their precious cargo. Before long, the trusty LM was released from the command module, remaining behind in lunar orbit. Now all that was left was for the crew to make the 2.5-day, 384,400 kilometer journey home. Something that was easier said than done. With every passing hour, Earth grew bigger and bigger in their windows, offering a tantalizing glimpse of home. But with the main aspects of their mission accomplished, they could finally turn their attention to a rather unsettling phenomenon they had all been experiencing. When they closed their eyes in the dark, the astronauts saw something strange, brilliant flashes of light that shouldn't have been there. Buzz Aldrin later described them as spots, streaks, and supernovas. He recalled the crew fearing they might be signs of their own fatigue, or, more worryingly, a failure in the spacecraft's engineering. Luckily, in 1952, a physicist called Cornelius Tobias had predicted this very issue. He had been largely ignored, that is, until the astronauts started reporting these phenomena. Tobias theorized that outside the protection of Earth's magnetic field, high-energy subatomic particles would collide directly with the astronaut's eyes. As the particle passed through the fluid of the eye, called the vitreous humor, faster than the speed of light in that medium, it would create an optical sonic boom that would appear as a faint blue glow called Cherenkov radiation. Whilst the bias was not proven definitively right until 3 years after the Apollo 11 mission, these first observations sparked a wealth of research into this phenomenon across the subsequent Apollo missions. But even as the crew peacefully rested amidst the flicker of cosmic rays, they were accelerating into a lethal trap. At more than 39,000 kilometers per hour, the Earth's atmosphere loses its softness. Hit it at the wrong angle, and the air becomes as solid and unforgiving as a wall of stone. So how were they planning to get through? The crew's safety rested on two things: the path the mathematicians had mapped out, and the armor the engineers had provided, creating a vessel strong enough to survive the journey home. First up, the maths. Columbia had to hit an area in the sky known as the entry corridor. The target was a precise angle of 6.5 degrees relative to the horizon. The margins were unforgiving. If the angle was too steep, anything over 7.7 degrees, the capsule would dive too deep, too fast, and friction would generate temperatures far beyond the heat shield's limits. The deceleration would hit the crew with crushing high G's of force. All in all, not ideal, as the ship would likely incinerate. But if the angle was too shallow, under 5.3 degrees, the atmosphere would act like the surface of a pond. The capsule would jump off the heavy air like a skim stone and be flung back into an elliptical orbit. Whilst this doesn't sound too bad, you have to remember that the service module, the part of the ship that supplied the oxygen, was planned to be jettisoned just before re-entry, so the crew would be trapped, drifting in a silent orbit, slowly suffocating to death. But even with a safe path through the corridor calculated, the journey was anything but a gentle descent. The crew still had to contend with white-hot 2,700 degree temperatures and crushing G-forces that pushed their human bodies to their absolute limits. These forces had to be absorbed, and NASA engineers had built the answer directly into the bones of the command module, starting off with its shape. Unlike a sleek missile, the command module was a blunt cone. This was a deliberate piece of hypersonic wizardry discovered in the 1950s. By being unaerodynamic, the air did not flow around the capsule easily. Instead, it compressed the air in front of it, creating a detached shockwave out ahead of it. This massive wall of air acted as a buffer, forcing the most intense heat to flow around the vehicle rather than into it. The heat that did touch the ship was met by one of the most sophisticated substances ever devised, Avcoat 502639, a low-density ablative heat shield material arranged into tiles that covered the bottom of the craft. This was no simple tile. It was a resin-filled fiberglass honeycomb that functioned through a process called ablation. As the Avcoat heated up, the material chemically decomposed, charred, and then flaked away, physically carrying the thermal energy away from the spacecraft. But for this sacrificial chemistry to work, the shield had to be flawless. This wasn't a mass-produced component, it was a delicate mosaic. The Avcoat resin was injected into the structure, consisting of more than 300,000 individual cells. Any tiny air bubble or gap could lead to a catastrophic burn-through during re-entry, so the application had to be perfect. This perfection was not achieved by machines, but sheer human persistence, which continues to this day. Armed with specialized tools that look like industrial caulking guns, teams of technicians filled every single cell, one by one, by hand. After each cell was filled, the entire shield was X-rayed to search for the slightest imperfection. It was a process that took several months for a single capsule. and the result of this painstaking labour was a masterpiece of thermal insulation. While the outer shield glowed white hot and disintegrated in a stream of sparks, the aluminium pressure vessel and the 3 men inside remained at a comfortable room temperature just inches away. That was the theory anyway. All that was left was to actually do it. Columbia slammed into the air at around 40,000 kilometers per hour, the friction stripping electrons from the surrounding molecules, creating a shimmering sheath of ionized gas that blocked all radio waves. In Houston, the consoles went flat. 3 minutes. That was the duration of the blackout, a period of harrowing silence where the crew of Apollo 11 was encased in a cocoon of superheated plasma, unable to communicate with mission control. Inside the cabin, the view was apocalyptic. The windows were filled with a chaotic swirl of orange and neon green as their heat shield disintegrated around them. The crew were slammed into their seats, crushed by a 6.5 G force. Roughly 20 kilometers up, the fire subsided and the radio crackled back into life. Soon after, the apex cover was jettisoned and a pair of drogue parachutes snapped open to stabilize the plummeting capsule. Then, 3 iconic orange and white parachutes unfurled, slowing the near 5,000 kilogram craft from a terminal plunge to a survivable 35.4 kilometers per hour. 5 minutes later, at 16:50:35 UTC, Columbia hit the Pacific Ocean, around 1,527 kilometers southwest of Hawaii. Splashdown. They had survived the landing, but the nearly 2-meter high ocean waves they landed into were less than hospitable. Thankfully, one final piece of clever engineering called the uprighting system ensured they did not drown. Because the capsule had an offset center of gravity, it tended to settle in the water upside down, leaving the astronauts hanging from the ceiling by their seating straps. To prevent this, what looked like 3 giant yellow beach balls were triggered by the crew to force the ship to right itself. Now stabilized, all the crew had to do was wait to be rescued by boat. But as it happened, the ordeal was not yet over. Even as the hatch finally creaked open, the hero's welcome was deferred. Because NASA scientists feared that lunar dust might harbor unknown pathogens that could devastate Earth, the crew was not met by their families, but by a biological isolation team. In the middle of the Pacific Ocean, Armstrong, Aldrin, and Collins were forced into biological isolation garments, looking like silver aliens. They were whisked away in a sealed mobile quarantine van and eventually locked in a high-security lab in Houston. Behind a thick pane of glass, the men who had just conquered the heavens spent their first 21 days on Earth in a glorified cage, watching the world celebrate their triumph from the inside of a sealed room. Armstrong even celebrated his 39th birthday in quarantine, although the lunar receiving lab kitchen staff did make sure he got a cake. We often remember the names Mike Collins, Buzz Aldrin, and Neil Armstrong, but Apollo 11 was carried by an invisible tide of nearly 500,000 people. Every kilometer of the 1.5 million kilometer journey was paved not just with rocket fuel, but with the quiet, relentless expertise of a civilization working in unison. Apollo 11 was the ultimate accelerator. It forced a quantum leap in engineering, giving birth to the microelectronics and integrated circuits that power our modern world. It turned the impossible into a repeatable, industrial process, creating a blueprint for complex systems management that we still use to reach the stars today. But the legacy didn't stop at the splashdown. It was just beginning. The nearly 22 kilograms of rock and soil the Apollo team brought back fundamentally rewrote our understanding of the solar system. By analyzing the chemistry of the moon, geologists discovered it wasn't a captured asteroid, but a piece of the Earth itself, born from a violent planetary impact billions of years ago. Even 50 years later, the data still lives on. Hundreds of scientific papers are published every year using Apollo-era data, as new technology reveals secrets in the dust that the original scientists couldn't even imagine. Perhaps more on that another day. But for now, Apollo 11 wasn't just a journey, it was the ultimate proof of concept. It showed that when a species focuses its collective genius on a single, impossible goal, the quiet expertise of the many can push the boundaries of human knowledge forward forever. Hopefully, it won't be too long until we finally go back. Thanks for watching. If you've been enjoying Astrum's videos and want to help keep this channel thriving, I want to ask you to take less than a minute to check out the Astrum Patreon. It's not just ad-free videos, but it's a way to make Astrum's videos less reliant on sponsors and algorithms. The link is below. Your membership directly helps ensure that future videos can stay independent, high quality, and consistent, created for curiosity, not clicks. Thanks so much for considering it. I'll see you next time.